So thank you for coming to this session about presumably obscure technology called eBPF. In the first part of this talk, we are going to understand what BPF is and what it can do, and we're not. And in the second part, we are going to rather understand how to use BPF with our beloved Go language. So it has been since like 3 years that Brendan Gregg from Netflix described the BPF as the superpowers for Linux. And since then, the BPF has evolved a lot. The whole ecosystem has grew that much that today we have tools, libraries, frameworks, and a bunch of other things also in Go, or Go libraries, to work with the BPF. So you probably heard the term. Someone worked with a BPF. Someone knows what a BPF is. Raise your hands. Okay, 1, 2, 3. Okay, I can go away. Bye-bye. Joking. Let's start saying that probably almost anyone in this room already used the BPF, because BPF is in tools that we use daily, and maybe we don't know. So since we probably are not putting our hands directly on a BPF, we are not taking any stake in the huge amount of cool things that the BPF can do, but we are using it every day. So let me spend like one second presenting myself, if I'm able to change the slide. My name is Leonardo. I work for Sysdig. Among other things, in the past, I co-created kubectl Trees, which is basically a kubectl plugin to schedule on BPF, except for BPF Trees programs on your Kubernetes cluster. And today I work on Falco and CNCF tool for container native runtime security, and which, by the way, uses a BPF under the hood. But I'm not going to talk about Falco today. I just want to say that Falco exposed recently we started exposing Go API for Falco. So if you're interested in detecting security anomalies and having the alerts in Go try it. We have a public Slack who you can give us feedback, would be really appreciated. So BPF is not a new technology at all. It's probably older than half of the people in this room. It originates in 1992, and recently in 2014, thanks to Alexei at Facebook, it has been made available to user space and to a broader audience. I don't want to spend so much time in details. If you're interested, I will publish the slides so you can grab all the details about registers and boring things that I put here. So let's go on. Well, I was saying that almost everyone probably used a BPF without even knowing it. Do you ever use TCP dump? Yeah, you use the BPF, because the BPF filter expression gets compiled into a BPF bytecode, which is then loaded into the kernel. And so the filtering of packets happens at the kernel level, which is known to be more performant than doing it in user space. This way, useless copies of packets to user space are avoided. And eBPF probably does to Linux and will do to Linux what JavaScript did and does to HTML. So rather than having, for example, imagine a static HTML page when there was no JavaScript. Then JavaScript came, and you started defining many programs that run on events like shitty events like mouse clicks and stupid things like that, and which are then run in a safe virtual machine in the browser. eBPF does the same thing with the kernel. So instead of having a fixed kernel or having to recompile it, you can basically write many programs that run on events like disk outputs, network packets, things like that. Which are then run in a safe virtual machine in the kernel. So in reality, eBPF is more like V8, but no one codes in V8, right? I hope no one is that crazy. And eBPF is the same. Writing a BPF can be really, really hard. we will do in this talk, but usually the best approach is using libraries. For example, using a GoBPF library or other library in other languages to write it. So let me go on. I was saying exactly this, that the ecosystem has already provided a simpler framework for a BPF. For example, the GoBPF1 from IOVisor, which is a branch of the Linux Foundation dedicated to the BPF ecosystem. Also Dropbox started an effort in writing a GoBPF library, which is a GoBPF library for now only for XDP, a kind of a BPF for networking, filtering, and things like that. Then there is BPF Trees, which is, for example, a language, a simple language with one-liners that already provides you ready to use variables for a BPF and helpers, and so you can use that. And then there is the BCC, the BPF compiler collection, which is also included in the GoBPF library. And it's a set of tools ready to use that simplify the use of a BPF. So basically, with the BPF, we can run code safely in the kernel without having to write a kernel model. If anybody here ever wrote a kernel module, it can feel the panic of having it panicking your machine. And with the BPF, we don't have this problem anymore. So basically, BPF solves the long-standing problem of having the Linux kernel not easily programmable. But, okay, we are going to write some eBPF with Go, but what BPF is? Well, should be clear now that BPF basically is an architecture that allows you to write many programs that run on events, like basically events coming from all the Linux subsystems, like memory management and scheduler and things like that, that are then run in a safe register-based virtual machine that uses a custom, details, 64-bit RISC in instruction set in the kernel. The important thing is that a BPF emphasizes the safety. There is, in the architecture of a BPF, in the virtual machine, a verifier that basically does not allow you to write, for example, unbounded loops or to refer to pointers in bad ways to exceed the maximum call stack. And this clearly is a mandatory choice, was a mandatory choice for a BPF, because BPF programs come from user space, but you have to be sure that they cannot break your machine, your kernel. So there are a lot of things to verify before running them. We will see later how to make the verifier complain. We will verify the verifier later. So let me go on. I hate this. This is the architecture, the diagram of architecture I'm talking on. Basically, we have BPF source, which is can be really hard to write, as I said. We need to compile it. We obtain an elf, basically an object file, okay, which contains references to opcodes, maps, and other things. We use the BPF system calls to load it into the kernel, and into the kernel there is the verifier, which complains about things, and if everything goes well, the virtual machine executes our BPF. As you can see in the bottom of the slide, and on the right of the slide, there are a whole set of BPF program types. We will not discuss them because it's not the scope of this talk. But basically, you can write BPFs for networking reasons, like filtering packets or creating meshes, things like that. Or you can write program with the BPF for access control on C groups, or you can detect the calling, the entry and the exit of a kernel memory, a kernel function of you probe. For example, you have your Go program, your Go binary, which executes a function you want to detect from outside without touching your Go binary. Maybe you don't have the source of your Go binary. You only know that you want to, for example, detect the count values function or the main functions of your Go binary being called, and you can use uprobes or uret probes to do that with the BPFs, and so on. Here, just for reference, I put the various kind of BPF program types. You can use it like a reference if you want to start digging into the BPF world. I said maps. Probably no one noticed, but maps are the most compelling feature of eBPFs. Basically, they come to the rescue to share the state between the kernel and the user, and user space land. So basically, they are an asynchronous in-kernel key-value mechanism to send data back and forth from the BPF to your user space, and we will use later in Go to obtain our data. And there is nothing special about this map, aside from the fact that probably they are the most compelling feature of the BPF, because they allow you to grab data from the kernel. The operations are the usual. You have a key, a size, a value size, a type, and so on. Nothing really new. Also, eBPF provides also helper functions. Differently from the initial BPF implementation, eBPF provides this whole set of functions, helpers, things to allow a various kind of applications, not only network packet programs. So let's start approaching how to write an eBPF. We cannot use unbounded loops. We cannot use global variables. We cannot passing struct to as function arguments and so on, because otherwise the verifier will not be happy. I said that the second step was obtain the health. So how do we obtain an health file? Fortunately, we have Clang, which is part of the LLL front end, a compiler for C++, Objective-C, and other, which saves us from the jungling with the raw eBPF bytecodes. And we obtain with Clang an health file, which basically contains all the references to opcodes, maps, and things that we need to. Sorry, someone is tweeting on my phone. No worries. Okay. Once we have loaded our BPF, we obtain a file descriptor. With that file descriptor, we can attach our BPF to an event. For example, we can attach a key probe to track a kernel function, the kernel symbol table, or we can use a new probe to track our Go function being called or not. And if the verifier is happy, the BPF virtual machine just in time compiles the BPF bytecode to native code for really huge performances, and that's it. We can enjoy it. So this is some of the things that we can do with the BPF, like examining the function return value with U, which stands for user space probes, uret probes, and kernel return probes. Or we can we can look at the context a function or eBPF is being called. For example, the context, the PID, the user ID, the thread ID, and things like that. The arguments of the function. So let's start approaching a concrete example, and I don't want to bother you anymore about technical details of things like registers and something. So this is a simple BPF, like 25 lines of code. We have the definition of a map at the top of it. So there is this count map, which we flag with an eBPF helpers, which is called sec, which is simply a macro that helps us to flag the map in the health file that we will obtain. This way, the Go BPF library can know where the map is and grab the BPF bytecode to execute. Same way we do for the socket program. We mark it with the sec helper, and basically we use some BPF helpers to obtain the protocol from the packet that we obtain. this is clearly a program to, I've not said, but there is the title, to count packets. The packets that we, the arrival of packets, we count them by protocol in a map. So we will end up with a map like TCP, 25 packets, UDP, 3,000, and things like that. We use the helper for looking for elements in the BPF map, and then there is this if. This if is really, really important for the verifier, because if you omit it, the verifier will not make you able to run the program, because there is a situation, the initial point, where the pointer can be nil. And so you need to account for that. Another thing that I want to say, which is really important to say, is that you need to specify the license, and the version not, you don't need, but the license you need to specify, because BPF doesn't run not GPL compatible programs. So you need to say that your BPF is GPL. Yeah, there's something really, really strange about this, but there's in the source code in the Linux kernel, because BPF is part of the Linux kernel, a part where they check this. So sometimes, not for all the kind of BPF, not for all the BPF programs, but for some kind, just put it, because otherwise we will spend hours understanding what's the problem, because it's not working for that. So, okay, this slide is not really well visible, but basically we compile with Clang the file that we just saw, and we emit intermediate LLVM representation, and we compile from that the object file. Then with readelf, we inspect our object file. We can see here that thanks to the sec macro, we have the license, version, count map, and socket program marked in the help file. So the GoBPF library, which we will use to load this object file now, knows where to find them. So we arrived to our beloved Go. We have this GoBPF library, which provides low-level routines and helpers to load BPF from help, and also provides bindings to the BPF compiler collection. We will see both of the approach. Basically, it defines a struct called module that represents the BPF we are loading. And as you can see, there are maps to refer to sockets filter, a kind of a BPF program, the one that I just wrote, maps, probes, probes, U probes, and other kinds of BPF programs. So basically, the convention is that he looks for sections with prefixes. So maps / something, it will use that like a map, or will try to use that like a map. Socket, as I wrote before, socket something, it will use that like a socket program, socket filter program. And I put all the references in the source code to see how it implements this. Clearly, there are also, it also looks for license and version. I forgot to say that the version is needed to use the current kernel. So if the version is that number, it will use the current kernel, otherwise not. Anyway, basically when we call the load function, it creates a module looking at those prefixes. And this is not pseudocode, I just removed the if and the else. Anyway, the code is, there is the link to the GitHub repository with the examples compiling and running. Basically, we provide the path to the object file, packets.o, the help file. We load it. That function will populate the module. And so if everything is good at this point, we can look for our packets map, because in the original file was called maps/packets, and while socket/program, the prefix is not removed here. Okay, we search for the socket filter to the socket filter program. Then we basically grab all the network interfaces of the machine where this is executed, and we attach the program to the interfaces, to the network namespaces to be correct. And this makes us able to count all the packet flowing on all the network interfaces. Then we need to grab the data that the BPF is, the data about the packets that the BPF is putting into the map. To do so, we write a poll function that basically uses lookup next element, which is a function provided by GoBPF that simply wraps any BPF helper, basically. That you pass the map, data is the map, and the key, the value, and the next key, and it simply iterates the BPF map, populating by reference key and v. And so we write these four that iterates until there are still elements in the BPF map, and then we poll on this function every x seconds for a max amount of time, so we can empty the map and receive the counts of the packets that are flowing towards the network interfaces. There's also another approach with perf maps about using channels, Go channels, to obtain data from BPF maps with the Go channels, but it's very similar to this. So basically, this is the result. If we have time, we will try it lively, and we end up obtaining a map, a simple map with the key 7, 6, 17, and the number of packets that we are receiving. 6 means TCP. Okay, this is not a really cool detail. But then I say there's another way to write BPF in Go. So write them directly in Go, not loading the health, but writing them directly in Go. Maybe I personally don't like it. There are people that like it much more. For example, you can simply define a string in your Go source code where you put your restricted C in. So you put your BPF in. In this case, I basically wrote a simple trace clone function. The scope that we want to obtain is to trace the programs that are calling the clone syscall. And we get with helpers the current thread ID, the current user ID, the current process ID, because we want to know what is the program that is doing clone, right? And at the end, we simply use another helper to debug, to print out this information to the trace pipe. Trace pipe is a component that you can find in a path that I will show soon. A component that you can use for debugging with the BPFs. So basically, you write this chi into a string into your Go file, and then you use always Go BPF, but the BCC sub package, and you pass the source to the new module. You create a module like before. You get the syscall function name clone, and load the key probe trace clone, the function that I defined in the slide before. When we did this, and if everything is okay, clearly you have to check for errors, the usual pattern for Go. You can attach the probe to that syscall. I did this with a key probe. Probably a better approach would have been doing this with a trace point, which is another kind of a BPF. I left this as an exercise for all, if you want to play, and maybe you can send a PR to the repo where the examples I'm talking about are. So this is the result. Basically, you make your program run, and in this path, which is the trace pipe path, you start seeing the debugging strings that we put there flowing in. I was saying the verifier. Yeah, the verifier is something that you need to be friend with, and otherwise, for example, if you remove the check on the pointer in the that we looked at before, the verifier will tell you things that you cannot understand. I probably no one can understand, but basically the reason is that he understands that the pointer can be nil and so can be incremented, and so it complains, starts ranting about it. So then another approach that is possible is to basically use BPF Trees, which is, as I said, a simple language about that wraps functionality for a BPF in an easily and more usable way to track your Go programs. For example, you can count syscall that your program is running. You can read bytes. You can track the page faults of your Go program using BPF Trees, which is always IO Visor project. So the takeaways of eBPF. Make kernels programmable again. Okay, probably not again. This is the first time that the kernel is programmable. And you can use BPF with a really wide range of kernel subsystems, basically all of them. You can trace almost anything from functions in the kernel, functions in your Go, in everything. The overhead is negligible because BPF bytecode is just-in-time compiled for your native machine code. So it's really, really fast. And it supports a lot of architectures already. It's event-driven, so it's something that you need to account, for example, also when using Go. This is the reason that the Go BPF library returns channels, because it's event-driven. There are also negative things. I mean, let's say negative. For example, it's Linux only. BPF originates in the Unix world, and nowadays there are parts for BSD and other, but it's Linux only, to be honest. So you also require a fairly recent kernel. I mean, okay, the first BPF to user space was kernel 3.10. But there was like almost nothing there. To start using it, you need at least 4.18, kernel Linux 4.18. To be honest, I think that a BPF still needs is exactly this one, the ecosystem in Go, in Python, in other languages, to make them more easily to use and to write, because you cannot write in that C every day. I mean, you will become crazy. And libraries need some love. For example, the Go BPF library, to give this talk, I needed to fix it, to send PRs, because there is no people at the moment that is enjoying fixing it, maintaining it, because it's a lot of work, free work. And so no one. Have been started and done, but at the moment, what I feel is that the libraries, the ecosystem needs some love. So in my opinion, if you're interested in contributing, in helping, it's a huge opportunity to start learning a BPF and doing Go at the same time too. So, if you want, anyway, there are a lot of other details about the BPF that I expressly avoided to tell in this talk, because otherwise everyone will get outside. And if you're interested in knowing more, I can suggest this book about my friend Lorenzo Fontana from me. It's all about BPF from the start to the end, and it has been launched today, right? So run buying it, and that's it. Anyway, we can look at some real code now. If you want, we can look at the code. Microphone. I want you to just show. I want to show just the BPF program that I was talking about and the way that we are using them in Go. Can you see it? Okay, basically, this is the count packets Go wrapper for the count packets BPF, which is this one. Okay. Then basically we wrap it this way using the health package of GoBPF. We instantiate the module. BPF is just the path that we obtain from the get BPF function, the path of the object file. We load it. If there is no error, we have all the things in the health mapped to the struct in Go, so we can basically assess them. We iterate all the networks, and we open a socket in the network namespace, and for every one, for each of them, we attach the program to it. Then we created basically a polling mechanism which calls the poll function every interval second for a maximum time of how long. And the poll mechanism is simple. It iterates until still, which is a variable we populate from lookup next element, is true. So basically this means that we empty the BPF map as it contains the counts of the packets, and we do nothing, we just print them to screen. So if we run it, basically, okay, we compiled it with makefile. Okay, the makefile basically use a bunch of code to compile it, to download the helpers, the BPF helpers. You have to, for having the BPF helpers, since the BPF helpers are part of a BPF but are not shipped with the kernel, you need to download the file. That is the reason of that call. Basically, I'm going to download from the Linux kernel for actual Linux, the BPF helpers, to use them. I put them in the file, and I can include them in the C++, in the C, sorry. Then basically I compile with Clang my files. And when obtained, I can do and we can start seeing TCP, UDP, IPv6 packets flowing, and the poll mechanism getting them from the maps and printing them out. Or we can also, for example, use hping tree to generate numbers more greater if we want. But anyway, I think that the concept is clear. Or we can use the other one. For example, the hello clone, hello world, I don't remember the name that I gave to it. Okay. Sorry, one sec. I'm not able to do with the one end. System looks. For example, who am I? Okay. Now we can go to trace pipe to see Look, all the clones that are happening, hello clone, yes. The trace pipe format is not really cool, but anyway, you can, it's a file. You can read it in Go and print it in Go. But basically, all the, when I opened another tmux pane, all the things that my environment has, it started cloning GPG agent, the shell, and so trace pipe started outputting it, for example. And that's it. You can write all these sort of obscure programs with the BPF, wrap them in Go, write them directly in Go with BCC, compiling them on the fly and running it, and that's it. If you have questions, things that you will know more, please ask. Tell me.
Your repository is private. Can you make it public?
Sure. Right now.
Thank you.
Then? Other questions? No?
You mentioned that you prefer the compiling your BPF code with Clang directly versus like inlining it and using libc to compile it. Is there a reason why you prefer one way or the other?
I prefer having it, compiling it with Clang and then loading it from the hub in Go. Simply for a simple reason. This way you have the object file and you can load it in Go, in Python, in other languages. Having it directly in Go, for example, doesn't give me, for example, a stupid thing, highlighting the restrict C, which is something that helps me when you write C, or doesn't give you auto-completion for BPF helpers, for example. Rather, if you write restrict C, yes, it's not that cool, but you can then use the help file with other frameworks, and while you're writing it, it's simpler, in my opinion. That's it. Any other question? Ale, you have other questions? No? I know you have.
So when can we write our BPF programs in Go?
If you want, we can start contributing to that library right now.
Well, I mean the actual BPF bytecode itself being out from Go source code.
It's we are still far from that. Still far from that. For now, what we have is basically a Go library, which can load it from help, or the same Go library that can basically use BCC, which is, by the way, a tool written in Python that does that. So it wraps another library. As I said, libraries need some love. And
What languages can we use to write the BPF bytecode?
the BPF bytecode,
What you were just talking about?
you cannot write BPF bytecode directly. You can generate it.
That's what I mean. Which languages?
BCC, for example, which is not a language, is a compiler collection for BPF written in Python, which Go BPF wraps and uses it to compile BPF in the const string on fly and then run it. Any other question? Nope. It's all. Thank you. Thank you.